student, welcome to all of you in the next physics lecture. This is the video number 34. Myself, Rajesh Lakat, physics teacher. Now I have to see here the chapter number 5, oscillation. Now we are to see here the very important topics, the energy of particle performing SHM. We have to show here the total energy of particle performing SHM is always conserved or constant. For that purpose, we have to see here the two energies, kinetic energy as well as potential energy. And sum of these two energy is nothing but the total energy. And this total energy of particle performing SHM, which is always conserved, we have to see here. For that purpose, we have to draw a diagram for the straight line Mn. We have to consider here the particles of mass m performing SHM along the path Mn, that is the straight line. And this is a point P with any point at any instant situated at a distance x from this mean position. P with any point situated at a distance x from the point O. Then we have to find here the first the kinetic energy, then potential energy, and finally total energy. First of all, the kinetic energy. For that purpose, we have to see here the expression for acceleration, velocity, and the displacement. We know that acceleration is equal to minus omega square x. Then velocity of the particle performing SHM, which is nothing but v is equal to omega under root s square minus x square. Therefore, the kinetic energy of particle, which is given by the k is equal to 1/2 mv square. In general, the kinetic energy, we know that the formula for the kinetic energy is given by k is equal to 1/2 mv square. Then substituting the value of the v, that is omega under root s square minus x square. Substituting this value, we have to squaring on this side, that the v square, this is nothing but the omega square root is removed, and s square minus x square. Therefore, directly we have to substitute here 1/2 m omega square into bracket s square minus x square. We have to write here the split these terms. Kinetic energy is equal to 1/2 m omega square s square minus 1/2 m omega square x square. And this is nothing but the equation number 1. And this is the kinetic energy. We have to remember these terms. Kinetic energy is nothing but what? 1/2 m omega square s square minus 1/2 m omega square x square. Equation number 1. Now we have to find out the potential energy. We know that the potential energy, to find out this potential energy, the restoring force act on the particles at point P. The restoring force act on the particle at point P, which is given by the relation F is equal to minus kx, where k is the force constant and negative sign indicates that this force and displacement are opposite to each other, opposites with each other. And therefore, suppose that particle which is displaced through the small displacement, infinitesimal displacement x, through the small displacement x against the restoring force, then there should be the work done. And this work done is given by the dw is equal to minus f into dx. For small infinitesimal displacement, we can write here dw is equal to minus f into dx. Then substituting the value of this f is equal to minus kx, then dw is equal to minus sign is here, value of the f minus kx into dx, and this minus plus kx into dx. This is nothing but the work done. But we have to find out the total work done. To find out the total work done, we can integrate this equation. We know that this process. To find out the total work done, we can integrate above equation. Therefore, integration of dw is equal to constant k integration from 0 to x dx. We know that this formula for the integration x raised to n dx is nothing but x raised to n plus 1 upon n plus 1. So that we can directly write here k is a constant, and integration of x dx, x square by 2, substituting this 0 to x square by 2. And therefore we can write here integration of dw, that is the w, and w is equal to 1 half k x square. This 2 is here, 1 half k x square. This is the work done. But again we also know that this work done is always in the form of potential energy. We know that this work done which is always in the form of potential energy, and therefore we can write here this V, that is the potential energy, is equal to 1 half m omega square x square. This is the potential energy. PE instead of V, we can write here P is equal to 1 half m omega square x square. This is the potential energy in the form of work done. This is the equation number 2. Then we have to find out the total energy, which is nothing but the sum of kinetic energy and this potential energy. Kinetic energy, this is the equation number 1, and this is the potential energy in the form of V, in the form of work done, that is equal to 1 half m omega square x square. Then substituting this value, total energy E is equal to kinetic energy 1 half m omega square s square minus 1 half m omega square x square, substituting this value, and potential energy, that is the PE is equal to 1 half m omega square x square. Then plus 1 half m omega square x square minus 1 half m omega square x square. This term should be the cancelled, and remaining term, that is the total energy, E is equal to 1 half m omega square s square. This is nothing but the equation number 3. Remember here, we have to first find the kinetic energy, then potential energy, and then total energy. Total energy is nothing but what? Sum of kinetic energy and potential energy. Then the total energy we have to obtain here, the 1 half m omega square s square. As the m, omega and a, all these terms are the constant, so that E is equal to constant. That means the total energy of SHM is always conserved. Total energy of particle performing SHM is always conserved. We have to show here. Now also substituting the value of omega, that is nothing but the 2 pi n. We know that in first chapter we have to see here the angular velocity, that omega is equal to 2 pi by t, or instead of 1 upon t we can write n. Therefore substituting omega is equal to 2 pi n in here, this equation number 3, we get E is equal to 1 half m. Instead of omega we can write 2 pi n square and a square. Then taking the square of this 2 pi n, 4 pi square n square, simplest form. Then remaining term E is equal to 2 pi square m n square s square, and this is the equation number 4. E is equal to 2 pi square m n square s square. This equation shows that, we have to ask sometimes in your exam, show that the energy of particle performing SHM is directly proportional to square of amplitude and square of frequency. For that purpose we have to find out this expression E is equal to 2 pi square m n square s square. This equation shows that the total energy of SHM is directly proportional to mass, square of frequency and square of amplitude. This is the equation number 4. Understand this? And last one, we have to also find out this, some of the special cases for this energy of SHM. And first case is at the mean position. At the mean position, the x is equal to rest position, that is the 0, and the velocity is the maximum. Substituting this value, x is equal to 0 and velocity is the maximum, then the kinetic energy Ek, so we have to write here Ek, that is the maximum, 1 half m omega square s square. And potential energy at the x is equal to 0, therefore this potential energy is minimum, that is equal to 0. At when the particle is at its mean position. When the particle is at its extreme position, then the velocity is equal to 0, and this displacement x is equal to plus minus a, that is the amplitude. Then at the extreme position, substituting this velocity 0 and x is equal to a, we have to find the kinetic energy and potential energy. Therefore kinetic energy is Ek, that is the minimum, because we have to substitute the velocity v is equal to 0, then kinetic energy is minimum, that is equal to 0. And the potential energy, that is the EP, substituting the x is equal to plus minus a, this EP potential energy is maximum, and that is equal to 1 half m omega square s square. This is the special cases for the this energy of particle performing SHM. Also, which is seen in the diagram in textbook for this energy of particle in SHM, and you can draw this diagram if you have to ask the special cases for the mean position and extreme position. Okay, you have to understand this energy of SHM. Thank you.